the amount of calcium you need is pretty small. And so, you'd have to be really, really depleted. There's a low calcium model of epilepsy, which is weird, right? You would think, hey, we remove all the calcium and all the neurons would stop releasing neurotransmitter, so you wouldn't get seizures. But it turns out in the slice, you remove all the calcium and you get really nice seizures, but they're not synaptic, which is really weird. And the hypothesis is, and this is, I don't really get this, so bear with me. The idea is that calcium actually sits next to the membrane and makes the gradient across the membrane slightly, it makes the effective thickness of the membrane a little thicker. And that makes the gradient smaller. And so, is that right? No, I guess it makes it actually higher, so it makes the cells more sensitive to inputs. It keeps them closer to threshold. And you remove those calcium, and now only sodium sitting next to it, which is only monovalent. And it changes the gradient. So the voltage seen by those channels seems to be different. It seems like it's actually depolarized the cells now. And they become more sensitive and more likely to fire. So it's a very weird argument, but removing calcium seems to actually make cells more excitable, even though you've removed all the neurotransmitter release. I don't know. So you actually do see seizures in people who have low calcium. Plasticity is a really complex topic, and it's everything, all the modeling, is sort of assuming sort of static synapses, and then in the last 10 years now everybody's adding in dynamic synapses that have long-term potentiation and short-term depression, and you start getting really interesting dynamics out of models as all of these things are changing with time. And hopefully we'll get to the point where we will add synapses in. I will talk about that on, maybe I have just a second or two now. Have we talked about how to do synapses in the Hodgkin-Huxley model? So the next week you're going to add in synapses, I believe, right? So we have a vector which is dv, dv dt, and we have dn dt, dm dt, dh dt. Okay, so that's the vector we have, we send out of our Derivs function, right? And so in our synapse, we have these currents, and I said, well, we have another synapse here, and we're going to put in, similar to this, I'm going to write it down here, similar to this, a gating variable, okay? And these gating variables are going to be, I'm actually going to put in something like a g syn max, and then we're going to have a gating variable, which I'm going to call f times s times v minus e syn. Okay? And essentially, the df ds is equal to, or dt, sorry. We'll call this the fast. Oh, I'm sorry. This isn't right. Let's see, let me think through this. The f dt is equal to minus f over tau f, and ds dt is equal to minus s over tau s. And the idea is we set, like through the initial condition, the s and f variables to 1. So we set s at some time, the time of the synaptic input, so this is t naught, and then it's going to decay away. And then we have our fast, and it's going to decay away fast like that. And if we take s minus f, so this is f minus, or s minus f, s minus f, you will see they start off both at 1. And so that starts off at 0, and then they'll come up, and then it'll decay back down here. And this is called an alpha function. So what we do is we run our model, our Hodgkin-Huxley model, up to a certain point where we want to simulate a synaptic input. And then we take the initial conditions. So we have some kind of initial conditions. So we put ds, dt, df, dt. We run our simulation up to some point. So we have t equals 0 up to the time of our synaptic input. And we get out our values. So we might have something like minus 60 is the voltage. We might have 0.9 is the sodium potassium activation, 0.1 is the sodium, 0.2. So those are M, N, and H values at some point. And then we find these guys started off at 0 and stayed at 0. Okay? And now we add 1 to that. So now we change this to 1s there. And then we use this now as the initial condition for the next run. And now that's going to make these values go off, to decay back down through this dVdt, these equations here. They're just going to exponentially decay, but it's going to cause a conductance to come into the model. And by stimulating periodically, you actually can get these guys to actually get larger. If it hasn't decayed back down to 0, if you stimulate shortly afterwards, you're going to find this value is not 0. We're going to add 1 to it. It might go up to 1.2, and you're going to actually see something like, so here's the time of the first stimulus. You see something that looks like that. If you put in a second stimulus, now here, this value, the S and F values haven't gone down to 0, and you'll see this add up, and then you'll see a summation of inputs coming in. So it's fairly simple to add in a synapse into this model. Does that make sense? We'll go over it again. Okay. And the last thing is, here this V, we think of this V as the voltage difference between the inside of the cell and the outside of the cell, right? We've always assumed the outside of the cells to be 0. But if we put in an electrode, and that electrode produces an electric field, it will change the voltage outside the cell. So really what we want is V out minus V in. And what we'll start doing is putting an electrode voltage as a function of space to calculate what the V in minus V out becomes that V. And we'll be simulating an electrode which will change the V out, which will then change this equation. And that's all we have to do is figure out what is the potential as a function of distance from the electrode and the amount of current being run across the electrode. And that will be like the second to last homework.